Hello and welcome to part 2 of step 16. So we're going to continue on with proving that triangles are congruent, and we're going to get 3 new shortcuts in this video. So the first one is called angle side angle. So it reminds me a lot of side angle side, except for the fact that instead of 2 sides and an angle, we need 2 angles and a side for this one. So if we started out by circling the triangle, we would have one arc at B and E. We would have this side BA and ED, and then we would have angle A and angle D. So notice 2 angles and a side, where that side is sandwiched between the 2 angles that we know are congruent. Okay, so our first proof is starting with, I gave you the statements again. We're just going to try to figure out the reasons. So we're always, remember, going to start each proof with our given. Okay, and then we're going to make sure it's labeled. Remember, we can't label anything unless we have a congruent statement. So the fact that QS bisects angle PQR, that doesn't really help us right now. It might help us in the future, but we can't label anything on our diagram. So we have PSQ, so if you still need to highlight, that's okay. I'm going to go from P to S out to Q. And remember, I marked this with an arc at the vertex. And then I have RSQ. Woo. That one right there. So we have those 2 are congruent, and we can mark ourselves an angle out here. Okay, next we have PQS. I'm going to mark this with 2 arcs since I've already used 1 arc. And then RQS. Okay, so obviously those 2 angles, kind of similar to the ones at S, they both have a vertex of Q. So there's definitely something going on at Q or at our larger angle. And if we look back to our given, it says that QS bisects PQR. So PQR is this larger angle here. And if it bisects, remember, if we bisect anything like a cookie or candy or, I don't know why I thought cake, I don't know why I'm into all the sugary stuff, but if something is bisected, we cut it exactly in half. So there's 2 types of bisectors, one being segment, one being angle. This would be an angle bisector because we're bisecting an angle. So you could just say definition of angle bisector. And that would give us another angle. Alright, last one, QS is congruent to QS. So when something's congruent to itself, it is a reflexive property. And that would give us the side. Okay, so from here, we're going to look at, okay, we've listed these in angle, angle, side. We don't have, that's actually one of our shortcuts, that's the next one we're going to go over, but we don't have that necessarily in our pocket yet to use, but let's look. We have our arcs that are black, the 1 arc, and then immediately following that we have a side, and then we have another angle. So see how this is kind of sandwiched here. We have this angle, we have this side, and then we have this other set of angles. So that side is going to go in the middle as we rotate around. So this would be angle, side, angle. Okay. This next one, I'm hoping it's more of an easier proof. I just wanted to kind of review flow proofs. So if you forget how those work. So flow proofs work where the statements are in the boxes and then we write the reasons under the boxes. So the given sometimes, most of the time, is split up, but sometimes it's easier to read because the given flows exactly into maybe a congruent statement. So you can see exactly what you're using from the given to figure out a statement. So first, let's figure out which ones are the given. So zx bisects wzy, that's this first one here, so we're just going to write given underneath, and then xz bisects, so that would be this one right here. Okay. And then we have that pink one, which we'll get to later. So both of these givens say the same thing, not the same thing, but very similar things, okay? So for the first given, zx is bisecting wzy. So we have wzy, this large angle, okay? And we're flowing into the fact that wzx, so this angle here, is congruent to yzx, this angle here. Conveniently, we just did one like this, so hopefully that's still in the back of your mind. But when we have a segment bisecting an angle, we just have an angle bisector. So this would be definition of angle bisector. Okay, very, very, very similar. Zx bisects yxw. Whoops. So yxw is that angle there. So the two smaller angles that zx has now created are the same. So wxz, this one here, and then yxz, this one here. So again, we have a segment bisecting an angle, so this would be definition of angle bisector. Okay, so the green one gave us an angle, the blue one gave us an angle. Now let's figure out the pink one. We have zx is congruent to zx. So anything being congruent to itself is always, always, always. That's hopefully one of the easiest ones. Reflexive property, and we've marked it. And that gives us a side. Okay, so we have two sets of angles, our green and our blue, and those two are sandwiching our segment that we know that is congruent. So we would have angle, side, angle would be our reason of congruence. Okay, our fourth shortcut is a lot like the last one we just did. It still involves two angles and one side, but this time the side is not sandwiched between the two angles. Okay, so if we started rotating around these triangles, we would have angle A is congruent to angle D because they both have two arcs. Then we have angle E is congruent to angle B because they have one arc. And then our side, notice, is not in between. Okay, it's outside. It's not between our highlighting of green and blue. It's on the outside. So that's when we use angle, angle, side. Okay, if it was sandwiched between the two angles, that's when we would use angle, side, angle. Okay. So this is a really short proof, but I just wanted to touch on, excuse me, one thing. You can probably see just from the statements. Okay, obviously we're going to have our given, which we can go ahead and label. Okay, angle C congruent to angle C without even looking at the chart. Hopefully you're like, oh, something's congruent to itself. That's reflexive. So from the first one, we have DAC is congruent to BEC. That's an angle. We also have a side. And then in number 2, we also have an angle. So without even looking at the figure, we already know we have 2 angles and a side. But now in our pocket, like I was saying kind of on the last one, we have angle, angle, side, and angle, side, angle. We're not sure which one to use because it depends on where that one side is in relation to the angles that we know are congruent. So if you had something like this and we were trying to figure it out, I would definitely recommend separating the 2 triangles. So I'm going to go ahead and do that just so we can label them and get a better visual of what our congruence postulate is going to be. So obviously they're not perfect, but you kind of get the idea. So this would be E, B, and C. And we would have A, D, and C. So I'm just going to go ahead and label them. So DAC is congruent to BEC. I know they don't look, my triangles are obviously not congruent, but it's basically that if we took this first one and we flipped it over, we did a nice reflection, it would be the other one. And then we have DC is congruent to BC. And then angle C is the same in both of them. It's the same angle, so there you go. So now we've already labeled our reasons and we've already said, okay, we know we have 2 angles and a side. So now we have to ask ourselves, is that side that we know actually sandwiched between the 2 angles that we know, or is it kind of hanging out by itself? And the answer is it's not in between the 2 angles, right? If it was in between the 2 angles, it would have to be this side and this side to be kind of in that sandwich, and it's not. So because it's not, as we would rotate around these 2 triangles, if I went from E to C to the side, that would be angle, angle, side. All right, we're going to do this one just to kind of practice a flow proof. It's not going to hurt you just to do an extra proof, because then we'll just have more to look back on as we do our practice. So we always label our given first. So RQ parallel to ST. And RQ congruent to ST. Okay, the given for the parallel, that's already labeled because of these triangles right here. Okay, remember those little triangles tell us that those 2 lines are parallel. And then we have RQ is congruent to ST. Those are already labeled with these tick marks right here. Okay. All right, let's start with the green one. So it says RQS. So R to Q to S, that angle there, is congruent to TSQ, that angle there. That's interesting. So we have a few different options because we don't necessarily, they're not the same angle, so we can't use reflexive. They're not really even near each other, which can kind of be confusing. But what I want to, obviously what the proof is telling us to look back at is the fact that RQ is parallel to ST. So because RQ is parallel to ST, notice we have the parallel lines and that transversal. Our 2 angles are getting caught in the pockets of a Z. So when that happens, we have alternate interior angles. So this would be alternate interior angles. Okay. The last piece is telling us RUQ is congruent to SUT. So it's not necessarily telling us we have to use the fact that we have parallel lines, okay, because our parallel lines aren't even included in our highlighting, but it is having to do with two straight lines, okay? When we have two straight lines, the angles across from each other are congruent because they're called vertical angles. Hopefully you remembered that one. Okay, so we have a side, we have an angle, we have an angle. So we're either going to pick angle, angle, side, or angle, side, angle. Okay, so we have to ask ourselves, is the side sandwiched between the two set of angles? And it is not. So we are going to use angle, angle, side, because that side is not between the two angles. All right, last one. This is a whole other section for this right triangle congruence theorems. We don't necessarily need to know all of the other ones, because they're all the ones we've just learned, okay? The only really new one is what we call hypotenuse leg. So, hypotenuse leg, obviously we have a hypotenuse. So this can only be used if we have a right triangle, okay? All the other ones can be used if we have any sort of triangle. This one can only be used if we have a right triangle, okay? And the reason that is because, I'll get to that in a second. I need to explain something first. So for hypotenuse leg, we have to have that the hypotenuse is congruent to the hypotenuse, so notice these two sides here, and then the leg is just another random side. Okay, so those two there. It doesn't matter which one, it doesn't have to be the longer of the legs or the shorter of the legs, just the hypotenuse is I guess that's not the correct plural, maybe, I don't know. But the hypotenuse has to be congruent to hypotenuse, and then a leg, one of the sides has to be congruent to the other side. When you have that, so like if we were naming these as how we were naming the previous four that we've already gone over, we have two sides and an angle. So that would be SSA, which if you haven't caught on already, if we flipped that over in a different order, it would spell a bad word. And remember, we're not allowed to spell a bad word. You're never going to have SSA or ASS because that's a bad word, and we're not going to write any bad words on our paper. So this is really SSA, but because it's a right triangle, we're going to call it hypotenuse leg. But remember, this can only ever be used for right triangles. So we'll just go over a quick example, and then we'll call it a day. So remember, we always, even with a right triangle proof, we always start with our given. Then we make sure it's labeled. So angle A and angle C are right angles. Beautiful, that's labeled. And then AD is congruent to BC. That is also labeled. So one of the extra kind of steps to use in order to prove that you're using hypotenuse leg is you have to state that you have a right triangle. When you acknowledge that you have a right triangle, then you're eligible to use hypotenuse leg. So how do we know we have a right triangle? That's because we have a right angle. So there's no like special theorem for this. It's not earth-shattering, hopefully, but we know that these two triangles are right because they have a right angle, which is just meaning we know the definition of what it takes to be a right triangle. Okay, and there's nothing to label there. That's just acknowledging, hey, we have right triangles, so we can use that hypotenuse leg eventually. Then we have DB is congruent to DB, so anything congruent to itself is reflexive. And then we're already at the congruence statement. ABD is congruent to CBD. So we have A and C are our right angles. We have AD and BC, which we were told from our given, that's going to be a leg. And then DB congruent to itself is the hypotenuse for these right triangles. So this would be hypotenuse leg. So obviously you're more than welcome to use any of these examples in any of your practice if you want. Feel free to go back. You can only do these proofs so many ways, just a heads up. So the proofs in the practice and worksheets and all that kind of stuff, they're going to be very similar to these proofs. So please use them to your advantage, use them as resources, and don't just think, oh, well, we're done with the notes, so I don't ever have to look back. These are a great resource because you can only really write these problems so many ways. So at the bottom here, I put all 5 shortcuts for you, just so you can have them all in one place. So in the previous video, we went over side, 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 and side, angle, side, if you forgot those already. And then the 2 that involve angles, 2 angles and a side are angle, side, angle, and angle, angle, side. And then we have our hypotenuse leg right here. Remember, the hypotenuse leg is the only one that has to deal with a right triangle. The other ones can deal with any sort of triangle. You can use them for a right triangle, but the hypotenuse leg can only be used for right triangle. And that's it.